In this video, we're going to try and resolve one of the issues from the previous video, namely the fact that we cannot measure the kinetic energy of each individual particle in a reaction system. To generalize, we can use a graphical representation called a kinetic energy distribution, which shows the kinetic energy of all particles that occur within a given reaction system, assuming that all particles have the same average kinetic energy, which again we know is temperature. What this means is that each kinetic energy distribution is the distribution of kinetic energy of all particles, assuming that the temperature remains constant. So again, we're just going to assume that the temperature of this reaction system is 37 degrees Celsius, and that even though the temperature, the average kinetic energy is 37 degrees Celsius, we can see using this distribution that not every particle has this exact temperature. So the variables that we put on the y-axis and x-axis of a kinetic energy distribution are, on the y-axis we have the number of particles, and on the x-axis we actually have kinetic energy. So what this means is that as we go higher, as the amount of our kinetic energy increases, if we assume that the average temperature is 37 degrees Celsius, that means a relatively small number of particles are going to have a much higher kinetic energy, and most of the particles in this reaction system are going to have a kinetic energy around here. Now, if we were to look at the area under the curve, so if we shade in this entire curve here, the area under this curve represents the total kinetic energy of all particles within this system here. Now, as we can see, do all particles have the same level of kinetic energy? That is a resounding no. Now, what this means is that even though a reaction is possible above a certain temperature, let's say that the reaction in this system is perfectly possible at 37 degrees Celsius, because not every particle has the same kinetic energy, can all particles react successfully? Well, again, that answer is no, because depending on how much kinetic energy they have, maybe the particles that are down here will not have enough kinetic energy to react, while those up here will. So in order to measure how many particles, how many individual reactants are able to react because they have enough energy, we need another measurement which we call E-min. E-min, as suggested by the name, is the minimum amount of kinetic energy that is required for a collision to lead to a successful chemical reaction. And E-min, we don't know what E-min is in this case because we haven't defined what the reaction is. However, we can determine E-min experimentally, and we can determine that E-min is a constant for each given reaction. What this means is that each specific chemical reaction will require a specific amount of kinetic energy for its reactants to have in order to undergo that chemical reaction. Now, if we actually label E-min on our graph, let's erase the shading that shows the total kinetic energy, and instead we're going to represent how E-min would work. So again, we don't know what E-min is because we haven't defined our reaction, so I'm just arbitrarily going to say that E-min is here. Now, what this means is that all of these particles here, the area under this shaded curve, these particles here are the particles that do have enough kinetic energy to react, and therefore they can undergo a chemical reaction because, again, they have the minimum amount of kinetic energy required such that when they hit each other, they will undergo whatever the chemical reaction is. The unshaded area of the curve here, these particles do not have the minimum amount of kinetic energy in order to undergo a reaction, so these particles here cannot react. Now, from this default framework, we can make a few modifications to the curve in order to represent how changing certain variables, one of which is temperature, can change the overall number of particles that can be involved in a chemical reaction. So, as a review, if you think of different ways to make a chemical reaction faster, most people will think of increasing temperature first. Another variable that we can change that actually has representations on a kinetic energy distribution is by adding something that we call a catalyst. For those that don't remember the exact definition of a catalyst in chemistry, we will explore that when we take a look at its effect on kinetic energy distributions. Now, general review, as temperature increases, we know that the kinetic energy of particles is going to increase. Now, because temperature is, again, the average kinetic energy, when we increase temperature, we are increasing average kinetic energy. That's pretty straightforward. Because particles have more kinetic energy, that means that they're moving faster. That means that the number of collisions we would also expect to increase as well. So if the particles are going to be hitting each other more because they're moving faster, we would naturally expect to see more particles reacting, and therefore we would expect that the area under the curve that is greater than E min is going to increase in size as well. And the way that we modify a kinetic energy distribution is with a vertical stretch, which in this case, because this curve looks a little bit strange, it will look like this. So here, basically, the peak of the curve has shifted down, and more of the area that is spread out here is pushed that way towards the curve. And if we plotted that E min was here, we can see that before the temperature change, so again, let's designate this curve to represent the temperature of 37 degrees Celsius, and maybe we've increased this temperature significantly. Let's say that we've increased it to 100 degrees Celsius. If we look at the area that under the curve that represents the temperature of 37 degrees Celsius, that's a relatively small number of particles that are able to react. But if we increase the temperature, now suddenly that's a lot greater a fraction of the particles that are now able to undergo a chemical reaction because they have enough energy to react. For those that don't remember the definition of what a catalyst is, that definition comes in two parts. Number one, a catalyst is almost always going to be a chemical that speeds up the rate of reaction. However, the catalyst is not technically part of the reaction because it is neither a product nor is it truly a reactant, because the catalyst is always going to be left over after the reaction is done. So a catalyst is not consumed by the reaction. For biology students, they may know catalysts by a different name. Your body's biological catalysts are what we call enzymes, and they function more or less the same way. Now, catalysts work differently than simply increasing the temperature, because when you drop a catalyst into a chemical reaction, the catalyst itself does not cause a temperature change, which means that the average kinetic energy of the reaction is not affected at all because there's no temperature change. So therefore, if there is no temperature change, does a catalyst change the shape of what the curve is going to look like? Well, no, that's impossible because, again, we're not changing what the temperature of the reaction is. Instead, what the catalyst does, it affects E min. So if we assume that E min of the uncatalyzed reaction is down here, remember that a catalyst speeds up the rate of reaction, which means that more reactant particles are going to be possible to react. So what a catalyst does is, through a number of different means, it takes the E min, the minimum amount of kinetic energy that is required to undergo a reaction, and decreases it. So this is what we can call the catalyzed E min. And if we compare the amount of particles that can undergo a reaction in the uncatalyzed situation, we see that it's much smaller than the amount of particles that can undergo a reaction with a catalyst present. Now, people that are familiar with enzymes know that the job of an enzyme, your biological catalyst, is to take two reactants and bring them together more easily in a more favorable orientation, which allows them to collide with each other much more easily. And that would make sense based on the change in E min. We don't change the actual kinetic energy of the reaction, but it allows the reaction to happen much more easily because collisions are easier to do with a catalyst present, and consequently a much greater fraction of all of our reactant particles are more easily able to react. In the next series of videos, we're going to be looking at the counterpart to kinetic energy, which of course physics students will recognize as being potential energy.